Last time I was motivating how groups arise in physics in general by emphasizing that it is expressing certain commonalities. I am surprised one is here. Okay, expressing some commonalities between physical systems. Okay. These commonalities are relational. It is a relational statement between different systems. For example, you might have quantum states with the same energy, and they are related by rotation. For example, this one example is of hydrogen atom, various principal quantum numbers, levels of the hydrogen atom, or it could be simply orbits. Similarly, orbits of planets around the sun, elliptical orbits of the planet around the sun, which you may go from one to the other by rotations. Groups are coming to express these relations. So, arise to express relations between physical systems, and then they, in course of time, okay, starting already I guess from 19th century classical mechanics, they started playing a dominant role in theoretical physics, and they became really indispensable with the developments in quantum theory, work of Wigner, Bachmann and many others. But one should realize that, and I emphasized last time, that this is not the groups are somewhat groups can be too much to express relations. They may be too strong. We may not need the whole structure of a group to express the fact that there is some kind of a symmetry, or certain events are related to each other, or certain states of a quantum system are related to each other. You may have weaker statements, and one particular weak statement which I at least want to familiarize you with the language are these Hopf algebras. They are weaker. The statements which go into this are weaker than those in groups, but groups in particular are special cases of Hopf algebra. So group is a Hopf algebra. From the group, so Hopf algebra implies, how do I write it? Groups are contained, can be interpreted as something contained here. Okay, but Hopf algebras are more general structures, and they are now turning up in studies especially in condensed matter systems, phase transitions in statistical mechanics, quantum statistical mechanics. For example, when you study integrable models or phase transitions at critical, say second order phase transitions, and other words which you would come across in this context are things like Yang-Baxter equations and so on. These are somehow related to each other. My understanding is that for some reason which I don't completely understand, okay, this kind of relational aspect has got formalized to a considerable extent in mathematics, and from what I have seen, this whole business of category theory, which of course we are not going to use at all, seems to be one tremendous formalization of what is happening in physics for a long time. But I should also say that this business of category theory has found practically no application in any realistic sense in physics. Wait till the end of the course. Qualitative, the most important thing we drop is the existence of an inverse. And deviating a little bit, when we do quantum mechanics, we deal not with, suppose you do angular momentum theory. In angular momentum theory, what you are doing is you have some G, which is a let's say SU2 or SO3. Okay, rotations. I will tell you why already in angular momentum theory we are abandoning notions of inverses. What are we doing? Then this is acting on some by some unitary operator on some state of angular momentum J. So this is dj m prime m of G, but we are not dealing with this because we take linear combinations of these objects. So we deal not with this, deal with not just UG, but we very often we take some set of GI and multiply by complex coefficients as summation I. Okay. We take linear combinations of these objects, okay, of these matrices, but when you take linear combinations, this object here is no longer invertible. I can take coefficients so that eigenvalues become 0. So this object no longer belongs to the group at all. It is belonging to what is called the group algebra, which we will come across, and this can be interpreted as some element of a Hopf algebra, these linear combinations. So a Hopf algebra does not even require that it is coming from an underlying group. So it is a generalization in that way. Okay. So basically invertibility, but there are other things. Okay. There are other structures which go into the definition of the whole thing. We use it, but we don't formalize it. But now people know how to formalize it. Now the one most important thing of, I would say, this from the practical, from a physical point of view, in the study of the group theory, I would say, then I will go on to continue what I was doing last time, is undoubtedly the fact that even though the physical rotation group is SO3, where the 2 pi rotation is +1, does nothing, 2 pi rotation around any axis does nothing. I would say the most important physical consequence has been the discovery by an analysis of groups and of the epistemology of quantum theory, that you might have a generalization where this group, which I will now explain to you, this becomes -1. Okay. I emphasized this last time, and this possibility, which exists only in quantum theory, means that you can have spin half, and then by some more sophisticated arguments, you have the notion of the Pauli principle, the Pauli exclusion principle, which is at the basis of practically everything that we can imagine. Okay. For example, the entire magnetism is based on this, that we know. Okay. Then Pauli principle is also very basic, for example, for stability of matter. Okay. I do not mean the Chandrasekhar limit, but just take a matter with both protons and electrons. Okay. The electrons and the protons attract, protons and protons and electrons repel. Okay. So the issue that arose was, why is this thing stable? Why doesn't it become much smaller? Okay, because of the attraction between electrons and protons, and how is it balanced out by the repulsion, and what other principle is required? This problem, I believe, was posed by Ehrenfest long ago in 30s, I believe. Okay, and it was revived, and the proof of the stability of matter as coming from Pauli principle was given by Dyson and Lennard. Okay. That is the first proof with very crude estimates, but it was not an easy proof, and later this was made very precise by people like Lieb and Thirring and many others. And the underlying thing which is absolutely essential is the Pauli principle, which says that the wave function of the electrons is antisymmetric and that of the protons. If it is not there, matter will collapse to much smaller sizes. Okay. If you use some other set, suppose you symmetrize the electron wave functions, it will become much smaller, and this is one of the most sophisticated pieces of analysis using just quantum mechanics. So this is not what I have talked. There is another thing called the Chandrasekhar limit for stars. This is not it, this is something else. And I also said this example, which I like very much, that which is very puzzling, but I mentioned it last time, that we know that most of space is empty. Okay. Atom is of size 10 to the power of -8 centimeters. The electronic orbits are of that order. The nucleus is about 10 to the power of -13 centimeters. So there is a huge area of empty space in between. Okay. Then the question arises, why I cannot take one finger, which is mostly empty space, and take another finger, mostly empty space, and cross one against the other. Okay. Zoom. Why can't I do that? Okay. Of course, you may claim that there are people in our country like Swami Ramdev and so on who can do such things, disappear from here, reappear from somewhere else. Okay? But just physicists, why can't we do this? Okay? Why can't all of us do this? And this appears to be related exactly to the Pauli principle. So there are macroscopic manifestations of the Pauli principle in our everyday life. Besides issues like stability of chemical matter, stability of our body, and so on, there are other ways also we can see it in a crude way. So last time, so this is by way of remembering for you, okay, what I was saying, the principal points I wanted to make. And last time I had given definition of groups. Okay, I defined what is meant by a group. Okay. Then I gave an example, namely the example of the permutation group. Sn. Then I also gave the example of the rotation group SO3 and O3 SO3. So these are 3 by 3 rotations. So let's say O3 consists of 3 by 3 matrices. Okay, let me use this notation. R transpose R is 1. This is simply meaning that this matrix is of size 3 by 3. R means it is real matrix is of size 3 by 3, fulfilling this equation, and the rotation group consists of these things. And we saw that this, because of this equation, delta R is plus minus 1, this, which implies this O3 can be written as a disjoint union. I will explain my notation very once more, where here the determinant is plus 1 and here the determinant is minus 1, and this P is a matrix minus 1 minus 1 minus 1, right? And this notation, Seema was asking this question, this notation is you multiply P with every member of the set. Okay? So this consists of all PR where R is in SO3. So this is a definition of this set. So I am multiplying each member of the set by P. Okay? We will need this notation later. Okay? So this means is a disjoint union. There is no common element between these two. Okay? If you just write union, there could have been common elements. So this is where we stopped last time. Okay? And we also generalized this to ON, and I told you that in O2, in even dimensions, something strange happens with parity. Okay? So let me not repeat it, but the notion of the way parity behaves in even and odd dimensions is somewhat different, and we also mentioned that last time. Now I want to say that in the notation that we come across, S, if you have S something, denotes special or determinant 1. Okay. So this notation will come repeatedly. So here the fact that there is an S here means the determinant is 1. Okay, so this is where we stopped last time. Now I want to go into example 3, SU2 U2. This group, which I will explain what is SU2, this has a very special importance in physics. Okay. So this consists of all 2 by 2 matrices G, and let me use this notation, 2 by 2 matrices over complex numbers. Okay. This means that these are 2 by 2 matrices, but the entries of the matrix are complex numbers, but the condition that it is U means unitary, so G dagger G is 1, U always will mean unitary, S means determinant is 1. let us we want to and we will spend time understanding this group. Okay, this is exactly the group which defines angular momentum, and there is a deep relationship of this group to the rotation group. Now by way of understanding this group better, okay, any G can be written as any such G. This is a very convenient notation. Z1 Z2 minus Z2 bar Z1 bar, okay, where summation Zi squared equal to 1. You can see that the determinant is 1. If you take it's obvious. Okay, the only question is the unitarity. You can easily check. Well, you have to show that the complex conjugate of this column is perpendicular to that column, which you can sort of see by inspection. Okay. So this is a unitary matrix, but we have this additional condition, and you can see that the determinant of G is exactly given by this, so it is 1. So you see from this equation that if I write Zi as xi plus iyi by separating real and imaginary parts and write this out, you find that this is the same as x1 squared plus y1 squared plus x2 squared plus y2 squared equal to 1. Okay, so this is a 3-dimensional sphere S3 in 4 dimensions R4. So the topology of the group SU2, as a topological space, SU2 is just a sphere in 4 dimensions, which we can see from here. Okay, whereas this is not the case with the rotation group. Okay, now let me see. There are questions, please ask. Now hereafter I will go more slowly. Okay. Okay. Now the unitary group. So in U2 we drop the condition determinant of G equal to 1. Okay. So it is simply G. So U2 consists of all G in this 2-dimensional matrix thing, but now it is simply determinant of G dagger G is 1. Okay, so we relax the condition which I have got here. So there is one extra degree of freedom coming from the determinant of G in U2, okay, which makes this group somewhat larger. Okay. This kind of group, for example, comes if you are doing particle physics, where the U1 here, which is coming here, plays the role of defining electric charge of particles. Okay, for example, of quarks. Okay. So I want to look at next example 4. The next 2 examples I give are almost foundational for quantum field theory. Namely, the first one is a Lorenz group. So this is, so call it L. So the L consists of all 4x4 matrices, but they are real entries. Okay. The entries of this matrix are real, okay, and it leaves where lambda leaves the quadratic form x0 y0. So let's write how to write it. let me write x transpose lambda y, x transpose eta y, I will tell you more clearly, is x0 y0 minus xi yi invariant. Let me, I will tell you slowly what I mean. These x's are real. So here eta is 1 minus 1 minus 1 minus 1. So it is a Lorentzian metric. The x's and y's are real. And by saying that this quadratic form is left invariant, I mean lambda x transpose eta lambda y is x transpose eta y. Okay. So this is the definition of the Lorenz group. You can check. Checking group property in all these cases is kind of trivial, so I am not writing it. These are matrix groups. Okay. Clearly identity is in this group. Okay. And if I take product of two of them, it will still leave the quadratic form invariant. So checking that it is a group is sort of easy. Okay. What is more difficult is recall, you remember, okay, note, recall O3 had two disconnected pieces. Right? We saw that because O3 was SO3 disjoint union PSO3. There is nothing in between. No, any 4 by 4 matrix, lambda is like just like the rotations let R transpose unit matrix R is unit matrix in 3 dimensions. I am just replacing 1 by this metric, indefinite metric, and you look for all of them. They are linear transformations which leaves this quadratic, which fulfill this equation. Okay, for any x and y, fix theta. Huh? Sorry, I am not hearing you properly.
Okay, it is true for two dimensions also.
You can define a 2-dimensional Lorenz group also. In 2-dimensional Lorenz group, I mean, it will be sort of trivial. 1 minus 1.
Yeah.
You can, the lambda, any lambda will be of the form cos theta, shin theta, then it will be minus shin theta, cos theta, plus this thing. Determinant, so it will be of this form because lambda, this equation here, so this equation says lambda transpose eta lambda is eta, like here. Okay. So if you take determinant, you see that the determinant lambda squared is 1 or minus 1 as usual, right. In 2 dimensions, likewise there is, you will find determinant is either plus 1 or minus 1, and the plus 1 piece will be simply a Lorenz transformation in one direction, because in one space and one time you can make Lorenz transformation only along the x-axis, right, one, and they are of this form, and for determinant minus 1 you can add minus 1 there. Okay. So you can define it in all dimensions. Okay. But what is more difficult, and we will do it later, that this Lorenz group we will prove much later, we will prove that this Lorenz transformation consists of 4 pieces. I will tell you what this is. Not so easy to prove. Okay. This one, okay, has time reversal. It changes. This arrow means down means it reverses the direction of time. Okay. So it contains time reversal. plus means it does not change orientation of the frame, spatial frame. So here it will be right like, so L minus down here has parity, so it contains time reversal, has parity P, and this contains Pt. Okay. So there are 4 and this one doesn't, this is the most harmless space. Okay. There is neither parity nor time reversal, just like in the O3 case the SO3 had no parity, no orientation reversal. Here this has 4 pieces, okay. And one can show this, but we will wait for that later. It's not so completely trivial to show this. You need some Short's inequality or whatever, then you can show it. Now I want to look at a group which is not a matrix group, it is origins, okay. And in some way, for sure, this is what underlies, I would say, all of known relativistically invariant quantum field theories. Namely, this is the case of the Poincare group. So the Poincare, let me call it P. Well, P is made up of, let me put it this way, of 2 things. One, A, these Lorenz transformations, but in addition it consists of space-time translations. So we want to know how to understand it. Okay. So to understand the group structure of this group, okay, let us denote an element of P. Okay. Let A lambda be an element of P, where A belongs to is a translation. So I'll call this as an element of 4-dimensional real vector space, and lambda will be an element of the Lorenz transformation. Consists of a pair. Now what is it? How do I find the group composition? Okay. To find group composition, okay, let us see how it transforms points x of real 4-dimensional space. Okay. So the not component, this x is time, and the other components denote spatial coordinates. Okay. So we say A lambda acting on x is a definition. We first Lorenz transform, so you get lambda x, and I translate. This is a convention, okay. So first Lorenz transform, then translate. This is a convention. If you do it the other way around, you can also do the other way around, you will get equations which are slightly different. Nothing much will change. They are just a notational change, so you can identify the groups. I will show you also rule for identification soon, in fact as I keep going. So I want to know how this is multiplied. So if you look at A1 lambda 1, A2 lambda 2, I want to know what this is to define the group abstractly. So let me see what it may do on a point x. The group action has to be associative. So this is by associativity. I will write this as A1 lambda 1 times A2 lambda 2 times x. Okay. So I work this out. This is A1 lambda 1 times, from this equation here, this is lambda 2x plus A2. Now I apply this again. So this is lambda 1 times lambda 2x plus A2. By applying the Lorenz transformation on this point of physical space, then I translate with A1. Okay. So this is equal to lambda 1 lambda 2 acting on x, right, from here, plus lambda 1 A2, let us write like this, plus A1, A1 plus lambda 1 A2. Right? But this is the same as this object here, A lambda, no? This is the same as A1 plus lambda 1 A2, lambda 1 lambda 2 acting on x. Okay. Let me see whether I am following. Yes, fine. Yes, fine. I just want to see whether I was following the notation in my book. Okay. So we find by comparison of this equation from here, we find immediately, let me write like this for the group, put a prime there, A prime lambda prime, A lambda, I am more comfortable with this, is equal to A prime plus lambda prime A lambda prime lambda. You get this multiplication law. Okay. So this is a composition law of the Poincare group, including first all reflections and in addition all translations. It is not a matrix group. There is no, this object is not, this translations that you are dealing with here, A is a translation. This activity is not a linear transformation on 4 dimensions because it does not leave the origin fixed. Okay, so it is not a homogeneous, it is not a linear transformation. Okay. So this is not a matrix group. Okay. And this particular way that the group is multiplying has a meaning. Okay. We will see that in detail later. Okay. When we look more, when we start understanding how this structure in quantum theory defines things like spin, angular momentum and so forth, okay, that this has a structure which people call as semi-direct product, but this now I am dropping this word, okay, for cultural reasons, but we will come back to it and understand what it is later. Okay. So this is it. I mean, in principle, let us say, if one starts from this group and tries to understand its implications, so this group and this realization in a quantum theoretical sense, okay, including supplement that thing with notions of locality, that is notion that experimentally we only have access to local things, we do experiments locally, okay, and causality, which is implicit actually here, it is possible to, these are the only basic principles, these are the really basic principles which go into the formulation of quantum field theory, okay. If you put these things in, but then you work for 50 years, you will get quantum field theory, okay. But these are the basic building blocks of quantum field theory, okay. So now I want to go and discuss, okay, how to identify, say the group may appear in many different guises, okay, but they may be the same thing in practice. Somebody was asking me what happens if I reverse these two things, the way I am acting, okay. Clearly I should not be getting anything new by that activity, so there has to be some rule for identification, and these rules are coded in these notions of isomorphisms and homomorphisms. So as a preliminary, okay, let me remind you something which undoubtedly you know. Suppose we have two sets, E and F. Okay. Then we can think of maps F, okay, which go from E to F. So a map is just a function, but the function normally we use it by saying that the value of the function is real or complex numbers, but there is no real reason for that. You can take any two sets and you can associate, okay, for a P in E I can associate a point f of P in F. But it should be well defined. It should not take a point P and split it into several points, okay. Then it will not be a function, okay. It will not be a mapping in the sense that we understand. So for each P there is a well defined answer in F, okay. There is nothing wrong in conceiving of a situation where a point goes into several points, but it will not be a map, okay. Such things happen actually in some physical context, okay, but we will not bother about them. You cannot call them a mapping, these are much more difficult to handle. Now I remind you that these mappings is one injective, right, if the image say called f of E, which is a set, simply the set of all f of P in F, okay, where P is in E. So I am just taking this E and see what comes out. It is injective if this is contained in F, okay. May not be, you may not get all of P, okay. So not every point of P, F may be coming from applying this F to E. So in that case we call it injective, and we say it is surjective. We say that if f of E is F, sur in Latin is onto, on, okay. Sur, Spanish, Italian, su means on, okay. So that is where this comes, okay. And we have this notion of bijective. Well, we have also the notion of let us say I do not know what 1 to 1, okay, means that this simply means that f of p equal to f of q implies p equal to q. So no 2 points, no 2 points of this E so you have this kind of a situation. This is not allowed in this case, okay. 2 points should not have the same image, okay. Then you have this notion of bijective. So this is or onto, if, okay. So finally bijective, if f is both is 1 to 1, call it n onto. Both these conditions are satisfied, we say it is bijective. A warning in maths books, they will add all kinds of footnotes about topology, okay, and continuity and so on. I will not, okay. For me everything is nice, okay. So I will keep going, okay. This is what we need to be able to do calculations. This much we should understand. Now why did I bring this up? Now these things, when I take it over to groups, okay, and homomorphism. So far as I know, again Latin morphos means shape, something like structure, shape, okay. So these are additional adjectives on how you are identifying things. So we are considering, we consider maps F from a group G to a group G prime, okay. Let me assume, okay, this will not cause us any trouble, that this F is onto. This assumption in our context will never cause any trouble. If you go into some infinite dimensional group, gauge group and so on, it can cause trouble, but here no. So I will assume that the image under F is G prime. What we are looking for in this F is, okay, we are dealing with groups. So we want to put conditions on F so that it preserves the group structure, okay. We want to put, put conditions on F so that it preserves the group structure. Okay. So what do we do? Okay. So case A. Okay. So this is accomplished by saying by requiring that if I take an element f of G prime, now this is living in G prime, say let me call it f of G1. So this is living in the image group G prime and multiplied by f of G2. So this is living in the image group G prime again, and the multiplication is in G prime. This should be the same as f of G1 G2, where I first multiply then apply f. Okay. So this condition is compatible with the group operations that we are dealing with. Okay. So you can write this in terms of a diagram if you want. Okay. G1 cross G1 G2. Well, normally it is write G1 cross G2. First I multiply. Take these two and multiply. Now I apply f here. So this is f of G1 G2. Right. Now here I first map them. So if you like, I can write this as a mapping f cross f. So this f goes here, this f goes here. So I get f of G1 G2 no f of G1 cross f of G2, sorry. Okay. Now I multiply them, put a thing here. Okay. So I get f of G1 times f of G2. Okay. I need space. So I multiply here, I get. So if I go this way and I go this way, I should get the same answer. Okay. So what people say is that this diagram commutes. So this is an example of a commutative diagram. Yeah. Sorry? This product, this is a product in the original group, this is a product in the new group, right? Because this is imaged. So the products that are happening here are different. Okay? But this f is intertwining the products. Okay? And people say that the mappings we are going to consider has the kind of f's we consider, which we consider as preserving the group structure, has this compatibility, or for them this diagram commutes. Okay. So this is an example of a commutative diagram, which commutative diagram is simply we put our knowledge in terms of a graph where we can visualize what is happening. Okay. And if you go this way or that way, you get the same answer. Okay. Now this is some consequences. First, if f is 1 to 1, well, first let me say, okay, implies A, if E prime are identities in G prime, okay. So the identity of G is E and the identity of G prime is E prime, then the identity of E under the map F is E prime. So identity goes to identity. How do I prove it? For this is an important equation. If I look at, well, I look at f of E, f of G, f of EG, but this is f of G. I am simply writing f of G. This is a product in G, but by the fact that f has this nice property, this is the same as f of E, f of G. but this is true, okay, and this, and since f is onto, so here I get all possible elements of G prime by choosing G suitably. F of E acting on any element of G prime is G prime, okay, from this equation, okay, all G prime, right. I simply choose, sorry, if there is something missing, what happens? Oh, I am overstating the case. Let me talk to you later. I am not very clear, but we will talk to you later. Anyway, we meet at dinner, so you can tell me. But the statement as stated is not wrong, so let me keep going. So we will find that f of E is E prime. Actually, in the similar way you prove the other way around. Okay. Similarly, the right G prime f of E is G prime. Second statement is the inverse of G inverse, which is f of G inverse. Okay. Again, we are using the this fact that f preserves the group operations, and I just use this sequence of identities, and you see that this f of G inverse is acting like the inverse of f of G, which is what we want. So this equation also follows. Now, before I start giving examples, okay, if f is 1 to 1, it is an isomorphism by definition. Okay. In this case, G and G prime as groups can be identified. Okay. At least in their characteristic as a group, then G prime as groups can be identified. Okay. So for example, if you do this, a lambda x is lambda x plus a, and then you take a lambda as a prime of x. You do first translate. Suppose I write like this. Somebody was asking that, no? If you reverse it, what happens, no? Because you consider a mapping from here to here, you check that it maintains the group properties, okay, the mapping, then the groups are the same. Okay. So it doesn't make any difference. Now I should give examples. Okay.
What do you mean by the groups can be identified? I don't really get it. What is the difference?
There is no difference. I'll tell you. Okay. I should say first, if it is many to one, I did not finish the groups are, I'll come please, are homomorphism. F is a homomorphism. Let me finish my statements, I forgot. Okay. In particular, if G equal to G prime, we can consider things going from one set G as a group into itself. Okay. Then replace iso by auto and homo by what? By endo. Okay. So the mapping is a group into itself, preserving the group properties. Okay. Then the words are changed. For example, if you can, some of you are familiar with, well, for example, what do I mean by, I should give examples, which I will. Okay. But in case some of you know particle physics, okay, then there is this classic example. Take SU3 of color, which are just 3 by 3 matrices, right? These are 3 by 3 unitary matrices. So these are matrices G, which are 3 cross 3. Then there is a standard operation, which is very often called charge conjugation. Okay. So I make an automorphism where I take G and goes into G star. I take the complex conjugate of the matrices. Not Hermitian conjugate, but you just take the 3 by 3 matrix and each element you put a complex conjugate. This clearly preserves all group laws because it's obvious. Okay? This is an example of a non-trivial automorphism that happens for groups, which is used. This is taking you a quark to an antiquark. To do this for 2 dimensions, you can still do this, but you can prove that you don't get anything new. Okay? Because there is something else you can do to recover what you had originally. So in 2 nothing happens, in 3 something new happens. Okay? So in 3 and higher something new happens. Okay? So that is an example of the kind of thing I am talking about when I talk about automorphisms. Okay? So now I will answer somebody's question. What was it? You were asking something. Oh, you will see it. There is no way you will miss it. It will be, I will show you, I will consider an example. Okay. Isomorphism is 1 to 1. Okay. In fact, I will be working out in detail a 2-1 homomorphism. That will be one of my next tasks. Okay. From SU2 to SO3. These are 2 by 2 matrices, complex 2 by 2 matrices which are unitary, and this is 3 by 3. How do I go from here to here? Okay. Is it 1 to 1 or is it many to 1? And we will see that this is many to 1. 2 elements here go to the same element here. So it is homomorphism, but we will see that it preserves the group structure. And furthermore, the meaning of this 2 to 1, where is this ambiguity coming from? This ambiguity coming from exactly the fact that if I make a 2 pi rotation in 3 dimensions, nothing happens here, but if I make a 2 pi rotation on a spinor, it changes sign. Okay. It is exactly that. Okay. So we will work it out in detail. Okay. So when this happens, either there are a lot of elements which disappear in the mapping, there are or if some discrete set of elements disappear in the mapping. Okay. In case it is a first case, it is easy to recognize what happens. Okay. The second case, you have to know. I mean, somehow you should expect something happening. Okay. There are rules for. If you are familiar with this, you know when it can happen. Then you look for that phenomenon to happen. Okay. We will get familiar with these things as we keep going. Okay. So let me just say in 2 minutes I will stop. Okay. Next I will see. Next. Okay. We will consider examples starting from the permutation group, okay, which appeared abstractly in terms of permuting objects and the linear transformations, and we had linear transformations LS, okay, where S was in Sn. Okay, I told you, well, one second please. Okay, I'll finish. So we had this equation, you remember LS LT is L of ST, where L were linear transformations in some n-dimensional complex vector space on a basis, okay, and Sn were S were permutations. Okay. I'll remind you what I did there. And we had a mapping like this. We had LS LT. Then we will see rather easily next time that this L is an isomorphism from the permutation group into linear operators on an n-dimensional complex vector space. I start with this example, which is quite easy. Then look at examples of automorphisms of groups, okay, which are, there are, all groups have certain automorphisms called inner. I will explain to you what they are. Then we will go into this nice example of SU2 and SO3. Okay. This is somehow central to physics, okay, both for non-relativistic quantum mechanics and condensed matter, and also it is central to quantum field theory. Okay. So I will work that out in detail. Okay. So that will be my project for next week. Okay.